Hello, welcome back. So I'm back with another video solution for one of the problems in the Math Wiz Quiz 4, which is Collegiate Math Quiz Bee simulation, which I hosted a couple of weeks back. For this problem, we are asked to find the maximum rate of change of the function f of x, y, z at the point 1, 2, 3. Now, in particular, the UP Mathematics Club nationwide search for a math wizard, which is a collegiate math contest in the Philippines. This question, this variant or this topic often is often asked in the competition. So if you are one of the potential or aspiring participants of the contest, I suggest you stick and watch this video or at least read more materials about the topic so you'll get maybe a point in the competition. So before we discuss the actual solution for the problem, let's discuss first um, what the rate of change is for a function. Now, for a single variable function, let's say f of x equals x squared, we know that the derivative gives you the rate of change of the function. So f prime of x equal to 2x gives you the rate of change of the function x at any point, let's say x naught. So x naught is equal to 2x naught. Now, if you're looking for the maximum rate of change of the function at the point where x naught equals 2, there is no point in that question actually, because there is only one rate of change in that function, and it's going to give you this derivative here. So there is no notion of maximum rate of change for a single variable function. The rate of change or the maximum rate of change arises for multivariable function. Let's say f of x, y, z equals x plus y squared plus z cubed. Uh, the rate of change is quite difficult to quantify at a particular point or at any point for a multivariable function, because you don't know how one variable behaves with respect to the other variables. The best we can do is we compute the partial derivatives of the function. So the partial derivative of f with respect to x is the derivative of this function if we treat the other variables constants. So basically, we have here the derivative of x, which is just 1. The partial with respect to y is basically the derivative of y squared with respect to y. And for the z, it's the derivative with respect to z of z cubed. Now it becomes complicated because we don't know how these three would interact. Because the partial derivatives only gives you the rates of change, assuming the other variables are constant. So, in other words, we want to find mm, the rate of change in a way or uh, or through or along a way where the relationship between the variables is defined. And we can do that by finding the derivative along a vector. So let's say we're looking for the rate of change of this function along the vector, let's say 1, 1, 1. So basically, we are saying here that the variables uh, move in a manner where they are, or the magnitudes of one is equal to the other, because um, the entries of the vector are equal. If it's instead 1, 2, 3, we say that y is in the direction that is twice x, where z is, on the other hand, z is on the direction that is thrice that of x. Did you get the point that I'm trying to direct? But anyway, that gives you the rate of change of the function along the variable or along the vector. Let's call this u. And we call that the directional derivative of x along the vector u. Generally, we want u to be a unit vector. So to find the unit vector of, let's say, this u, we divide it by the magnitude of the vector, which in this case is the square root of 1 squared plus 1 squared plus 1 squared, or simply square root of 3. So this is the unit vector corresponding to this one. So to find the directional derivative of a function f, we get this nabla of f, which is basically what we call the gradient of f, which is a glorified term for a vector containing the partial derivatives of the function. And then we get the dot product of this with the unit vector u. Okay? Now, now to go back to the question of what is the maximum rate of change, we can find that maximum rate of change by examining or using the properties of dot products. We know that the dot product of two vectors a and b is equal to the magnitude of a times the magnitude of b, the magnitude of a times the magnitude of b times the cosine of the angle between them. So this one means that this is the um, magnitude of the nabla of f times the magnitude of u. Sometimes I prefer writing 2 bars instead of one for the magnitude. I'm not sure if there is a strict difference between the two, but I am using them interchangeably. So it's up to you actually, or maybe I should read more. We should read more about this. But for now, I'll stick with the double bar notation, cosine theta. So the maximum directional derivative, which is the rate of change, is dependent upon the value of cosine theta. So we know that the value of cosine theta has a maximum value of 1. So this is max 1. Also, the value of the magnitude of u is always 1 because it's a unit vector. Therefore, the maximum value of the directional derivative only depends upon the magnitude of your gradient. So again, max rate of change equals magnitude of the gradient. You get it? Is that okay? So, if we apply this to the given problem, we have we have f of xyz equals xy plus yz plus xz. The partial of f with respect to x, which is f sub x as well, is equal to y plus z. Again, these are the only terms with x. So we treat the other variables constant and then differentiate, we get y plus z. Similarly, we get fy equals x plus d, and fz is equal to y plus x. Therefore, our nabla, which is our gradient of x, y, z, is equal to y plus z, x plus z, and y plus x. At the point 1, 2, 3, 1, 2, 3, this is y is 2, z is 3, X is 1, V is 3, this is 2, this is 1. So this is equal to, the gradient is equal to 5, 4, 3. Okay? So the magnitude of this gradient is the square root of 5 squared plus 4 squared plus 3 squared. We know that 4 squared plus 3 squared is 5 squared. So this is basically equal to 5 square root of 2. So the maximum rate of change is 5 square root of 2. And that's our final answer. Okay? So again, if you want the shortcut for this one, just use this concept here. The maximum rate of change is equal to the magnitude of the gradient. Now, if you want the minimum rate of change, you simply get the negative of this one. Negative for minimum. Okay? Is it clear? Is it clear? Now, there are other variants of this problem, or another related question for this one. Another possible question that can be asked for this particular problem is that along which vector does the function get or reach its maximum rate of change? To answer that, we only consider this gradient here. The maximum rate of change is always along the direction of the gradient. If you want the unit vector of that, just normalize by dividing by the magnitude. Okay? Is that clear? Is that clear? Is that clear? Okay. So that's it for this video. I hope you learned something from me today. If you have any questions, comments, violent reactions, or suggestions, anything, just let me know in the comments. See you on the next one, and bye bye.